Hi guys, welcome to this video. Today we'll be talking about electron configuration, orbital notation, and noble gas configuration. And I know it seems like a lot, but by the end of this video, hopefully it'll be a breeze to you. So before we get started, I would just like to define what electron configuration is. So electron configuration of an element describes how electrons are distributed in its atomic orbitals. So subshells do consist of these orbitals, and the four subshells that we know of is the s subshell, the p subshell, the d subshell, and the f subshell. In the s subshell, there are 2 electrons that can be held in each s subshell. In the p subshell, we can have 6 electrons. In the d subshell, we can have 10 electrons. And in the f subshell, we can have 14 electrons. And I'm saying all this because we'll get more into why it matters in electron configuration. But before we even get started on any of that, I would like to go over 3 rules that determine how we write our electron configuration and on our orbital notation and all that good stuff. So, Hund's rule says that every orbital in a subshell is singly occupied with 1 electron before the electrons start pairing up in the orbitals. And I'll start touching on all 3 of these rules more in depth in orbital notation because I feel like it makes more sense when we're talking about orbital notation, but I'll just give you a little bit of a direction here. So for Hund's rule, it says that every orbital must be occupied with 1 electron before pairing up. So say these dashes are the orbitals, and we'll get more into this, but this is actually the p orbital. So if we have an orbital like this, every electron, we'll use arrows, and I'll again explain why we use arrows later. Every electron must go into each orbital before pairing up, like this. So you can't go 1, 2, 3, 4, 5, 6. You have to occupy 1 in each before going back and pairing them up. And the other rules will also explain that, and also I'll get more into it in orbital notation. So Aufbau's principle says that electrons fill up lower energy atomic orbitals before filling higher energy orbitals. So each subshell has a different energy level. The s subshell has the lowest energy, next is p, next is d, next is f. So you have to fill up the s orbital before going up to the p orbital. You can't fill up a lower energy level before going to a higher energy level. So the last one is Pauli's exclusion principle, and that states that the paired electrons in the same orbital cannot have the same spin. In other words, one has to have a positive spin and one has to have a negative spin. So the reason I use opposite arrows in this example right here is because it shows that each electron in each orbital, which is this little dash right here, can't both be facing the same direction because they need to have opposite spins. So an orbital has to have electron going like this. They can't both be up like this or down like this. Okay, so this is the periodic table that shows the electron configuration, and I know it looks really overwhelming, but trust me, it's not as complicated as it looks. So I'll go more into it in the next slide about how we're exactly going to use this in electron configuration, but I just wanted to point out something. So as you can see, these little circles here, or just anywhere, shows how many electrons are occupying that subshell. So as you can see in 1s1, this basically says that in the first s orbital, there is 1 electron occupying it. So again, I'll get more into this in orbital notation, but that would look like this. The s orbital has 1 dash. This represents the s orbital, and that means there's just 1 electron like that. Now, in other case, the 1s2 orbital is the first s orbital that's given by the 1 right here. The first s orbital, and it has 2 electrons like this. And remember, they have to have an opposite spin because of the Pauli's exclusion theory. So that is actually a complete orbital, because like I said in the first slide, there can only be 2 electrons in each s orbital. So then after that, we would go down to 2s1, which is, and 2s1 on the periodic table is actually lithium. So I'll go ahead and actually give you the orbital notation for lithium. So if we're talking about lithium, that would be, if we're doing the orbital notation of lithium, we know that the first subshell, the first s subshell, is already completed because it already has 2 electrons in it. So we can just draw one little dash for s and put 2 electrons. But then there's only, in the second s subshell, there's only 1. So we'd only have like this, one electron. You can either go up or down. It doesn't matter. I always start with an up arrow, but it really doesn't matter. As long as when you pair the electrons up, they have a different spin. So one is facing up, one is facing down. All right. Sounds good. So that is basically the breakdown of why all these numbers are here. So now I'm going to show you a slide with like a side-by-side of the real periodic table and the electron configuration periodic table. And I think it'll give you more of a visual of how it all weaves in together. So as you can see, these periodic tables align with each other. So now I can really get into orbital notation, electron configuration, and noble gas configuration. So let's start off with some electron configuration. So if I was trying to find the electron configuration of, let's say, oxygen. Now, before I even tell you about the electron configuration of oxygen, I would just like to say that it is okay to use this electron configuration chart when you first start getting the hang of electron configuration. It does seem really overwhelming, but the more practice you get, the more you'll be able to use it without, because you'll see that it's just a pattern. And I'll point out the patterns as I go along. So we're trying to find the electron configuration of oxygen. So we would look and see which subshell correlates with oxygen. So that would be the 2p4. So, but we can't just write 2p4 as our electron configuration. We have to, in electron configuration, we're basically stating all the subshells that have been occupied and all the orbitals that are being occupied. So we would have to go back. We're saying, so the 1s2 subshell is occupied. So we write 1s2. Then we would go to 2s2. 2s2 orbital is occupied because oxygen is way past that, right? So we go 2s2. But then we can't go to 2p6. By the way, forgot to mention that you know when it's occupied because, like I said in the first slide, the S subshell has 2 electrons, the P subshell has 6 electrons, D has 10, F has 14. So you can just see when the subshell is occupied by those numbers right there. So we know that we stop at 2p4. So you just write 2p4. Now, how this would look in in orbital notation, it would be, so like we said, we know the 1s2 orbital is filled, so we write 1s subshell, and we would have 2 arrows going the opposite directions because the spins have to be opposite. And remember, we have to fill up the lower level subshell before we go over the higher one. So the 1s2 subshell is done, that's the lowest. And then we go to the next highest, which is 2s2, or right here. We're just going by the electron configuration. So then we'd have another s, and then we would have another 2 arrows going, because that's when it's also filled. But for the p orbital, we would have to... Oh, by the way, P has 3 dashes because each dash can hold 2 electrons, and 3 times 2 is 6. Same if we're doing D, which is 10, we would have 5 dashes, and then for F, we would have 7. That's why I'm doing the dashes. So for the P orbital, we stop at 2p4. So like, Hund's rule said we need to add 1 electron to each orbital before we start pairing it up. So when we add 1 electron to each orbital, that's only 3. We need 4, right? So we'd have to go back and pair it up and put an opposite spin to it, which means we had to put the arrow the opposite direction. So that's the orbital notation of oxygen. So noble gas configuration, it's very simple. It's even probably, I would say, even more simple compared to electron configuration, because we're just looking at the noble gases, and we are basically going to cut, I wouldn't say cut the electron configuration in half, but make it easier for us to write electron configuration. So if we're writing the noble gas configuration of oxygen, we would see what is the last noble gas. Noble gases is the last group, right? This one right here. What is the last noble gas that we passed? That we passed, and that would be helium, because even though neon is the closest, oxygen is before neon, so we can't say neon. So how we would write the noble gas configuration of oxygen, if we would put these little brackets around the helium, and we would just write helium like how it is on the periodic table. So we'd put helium, and then, which is here, so then we wouldn't even have to write 1s2, because the helium tells us that, oh, oxygen passed the one, already filled up the 1s2, and then we just go straight to 2s2 and then 2p6. So 2s2, oh, not 2p6, my bad, 2p4, and then 2p4. Okay, so let's do another example. I feel like the more practice you get, the more better we'll get at actually doing this really quick and not even having to look at this type of electron configuration, but whereas we can just look at the normal periodic table and figure it out. So let's do that. So let's pick a more challenging element to write with. Let's do nickel, so Ni. So let's start off with just plain old electron configuration. So we would start at the 1s2 orbital, and the reason we always start the 1s2 orbital is because that's the most completed. That's the completed one. And since nickel is all the way down here, we know that we finished 1s2. We don't have to even look at this. So we would go 1s2, and since nickel is so far down here, we also know that 2s2 subshell is filled. We know the 2p6 subshell is filled. We know the 3s2 subshell is filled. We know the 3p6 subshell is filled. We know the 4s2 subshell is filled, but the 3d10 subshell is not filled. It stops at 3d6. So this is what we would write. We would write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. That wasn't too bad, was it? So then we're going to do the orbital notation. So we represent the S subshell with 1 dash. So let's just write the dashes. So this would be S, this would be S, because we're just following like these. So this is the P. So 1, 2, 3, P, S, P again, 3, S, and then D, which is 10. So, 5 dashes with 10 electrons. D. Sounds good. Okay, so we know that the 1s2 orbital is filled, so we can just put those two opposite arrows. We know that 2s2 is filled. 2p6 is filled, because remember, how many electrons are in P? 6. Whoops, that's a little too much erase. Okay. So we would go 1, and I want you to, even though you know that the 2p6 orbital is completely filled, you should practice to just put electron individually in each orbital before going back. Even though you know it's going to be filled like this, you go ahead and put 1 electron in each of the dashes before going back, so you can fully prepare yourself for Hund's rule. And then we know the 3s2 is filled, 3 P6 is filled, 4s2 is filled, but 3d8 is not completely filled because the completed d orbital would have a 10. So we would first follow Hund's rule and put 1 in each, but that only gives me 5 and we need 8. So I have to go back. So this is 5, 6, 7, 8. So that's the orbital notation for nickel. Now let's do some noble gas configuration. So we would look at the last noble gas that we passed, which would be the 3p6. Also, if you haven't realized already, the completed p's and the 1s are all noble gas, because that's the easy way to figure it out. You just look at the last p that you filled out, which is the 3p6, and you go and you look what element is 3p6 or whatever p that you last filled out. So the last one was argon, Ar. So we write Ar in these brackets. So then we can forget about these. We can forget about everything up till 3p6 or after 3p6, and we just write 4s2 and 3d10. I mean, sorry, not 3d10. 3d8. Okay, there's one last example I want to do, because this one is with the f orbital, and when you're dealing with f orbitals, it's a little bit tricky, but hopefully with more practice it'll get better. So let me do one with more with an f in it. So let's do, actually it doesn't necessarily have to be an f either. We can do, let's do 4p, 6p. Let's do 6p. Let's do 6p5. I think that's a good one. So that would be, actually, let's do 6p3. That's a good one. So bismuth, Bi. So let's first look at what we've completed so far. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, don't skip to 4p6 without going to 3d10. Some people forget that. Then 4p6, 5s2, 4d10, 5p6, 6s2, and I love this electron configuration graph because it shows you when you get to when you go past these 6s2s and these 7s2s, you actually have to, these 5d1 and 6d1, you actually go down to the lanthanides and anthonides. So you actually bring this down. So you would go all the way to 4f14 because we're trying to get to bismuth, which is 6p3. So you have to go all the way down to 4f14, then go back all the way up to 5d10 and then get to 6p3. So that sounds like a lot, but basically remember that these two, when you get past 6s2 and 7s2, go down to the f's. And if you're trying to find the electron configuration of one of the f's, like let's say PM, which is 4f4, then you can just, as soon as you do 6s2, you can go down and write 4f4. But if you have to go back to the d's, if you're trying to find something in the 5d9s or even in the 6p's, you need to write 4f14 before going back up. And I know that's a lot, but That's the way it is. So we would go 4f14, then we go to 5d10. Remember, 4f14, then 5d10, not 5d10, then 4f14. A lot of people make that mistake. And then to 6p3. So this is going to be a really long electron configuration. So let's write it really quick. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Then we go down 4f14, 5d10, and then finally, I'm running out of room here, 6p3. That is a lot. And I'm going to go ahead and write the orbital notation for this. It's going to be a lot. So there's an S, another S, P, S, P, S, D, P, S, D. I might have to go down one more. P, S, and then I'm going to write the rest a little lower. There are 7 dashes in the F because 7 times 2 is 14. And then a P. That was a lot. So we know that all of these are occupied all of these that I wrote here are occupied fully until the P. The last one will most likely always not be occupied unless you're dealing with like 6p6, which means that noble gases are always fully occupied, like all the electrons are there, because noble gases don't need any more electrons. So yeah. So that is that. So we would write everything like, I'll just write this really quick. You can go ahead and write on your own and then check with me. Okay, and then when we get to the last one, remember we have to put an electron in each one before going back. But in this case, we only need 3 electrons because it's 6p3. So we're done actually. Okay, now to the noble gas configuration. So what is the last noble gas that we passed? And that would have to be xenon. So that would have to be 5p6. So you'd write this Xe. And then we would actually not write anything. We would not write anything until 5p6 or after 5p6. So then all we have to write is 6s2, 4f14, 5d10, and 6p3. And I think this will give you kind of a clarity of why noble gas configuration exists, is because if we have to deal with these big electron configurations for like some of these elements, it's going to be hard to write all of this. So an easier shortcut is to do noble gas configuration. And orbital notation is really just to show how the the 3 rules that we talked about earlier come into place, as you can see right here, like only putting 1 electron in each orbital before going up and pairing it up, and the negative spins, and how you can't jump to a higher energy level without filling up the lower ones. Alright guys, that's all I have for today. Thank you so much for listening, and I really hope this benefited you.